Welcome to this presentation on Retrieval Augmented Generation Architectures and Applications, presented by Dr. Suresh Veluru, Head of Data Science at Imperium Compliance in London. Today we'll explore several key topics in the world of RAG systems. We'll cover what RAG is and why it matters, examine the three main paradigms of RAG architectures, discuss how RAG compares to fine-tuning, explore augmentation strategies, review evaluation metrics, look at real-world applications, and survey the tools available for building RAG systems. Let's start with large language models. An LLM is a deep learning model trained on massive text data sets to understand and generate human-like language. The process is straightforward. A user provides a prompt, the model processes it through its neural network, and generates a contextually relevant response based on patterns learned during training. Now, what is RAG? Retrieval Augmented Generation is a framework that enhances large language models by integrating external knowledge retrieval. It combines the generative power of LLMs with the ability to access up-to-date, domain-specific information from external sources. This approach reduces hallucinations, keeps information current without retraining, and enables models to cite sources for better transparency and trust. Here's how RAG works in practice. When a user submits a query, the system retrieves relevant documents from a knowledge base, then augments the original query with this retrieved context before sending it to the language model. The LLM then generates a response informed by both its training and the retrieved information. RAG systems have evolved into three main paradigms. Naive RAG represents the basic implementation with straightforward retrieval and generation. Advanced RAG incorporates pre-retrieval and post-retrieval optimizations to improve accuracy. Modular RAG offers a flexible architecture with specialized components that can be combined in various ways. Let's examine naive RAG more closely. It follows three main steps. First, indexing. Documents are split into chunks, converted to embeddings, and stored in a vector database. Second, retrieval. The user query is embedded and similar chunks are retrieved. Third, generation. The LLM produces an answer using both the query and retrieved context. Advanced RAG improves upon the naive approach with four key steps. Pre-retrieval involves query optimization through rewriting, transformation, and expansion. The retrieval step uses fine-tuned embedding models and dynamic strategies. Post-retrieval includes re-ranking and context compression. Finally, generation leverages the refined context for better outputs. This diagram illustrates the key differences between naive and advanced RAG. Naive RAG uses direct query embedding and simple retrieval, while advanced RAG employs query rewriting, hybrid search strategies, and re-ranking to significantly improve result quality and relevance. Modular RAG takes flexibility even further. It introduces new modules like search, memory, fusion, routing, prediction, and task adaptation. These modules can be arranged in different patterns to handle specific use cases, making the system highly adaptable to various requirements. The beauty of modular RAG lies in its architecture. Modules can be organized in serial, conditional, or parallel patterns. The output from one module can serve as input to another, and different RAG paradigms can leverage these modules in unique ways to optimize performance for their specific needs. Fine-tuning is another important technique to understand. It involves taking a pre-trained language model and adapting it to specific tasks, domains, or styles through additional training on smaller targeted data sets. This process adjusts the model's internal parameters to specialize its behavior. This chart helps us understand the trade-offs between different approaches. On one axis, we have model adaptation, on the other, external knowledge. Prompt engineering requires minimal adaptation. RAG variants balance both dimensions. Fine-tuning focuses heavily on model adaptation with less reliance on external knowledge. Augmentation in RAG can take several forms. Single-time retrieval performs one retrieval operation per query. Iterative retrieval alternates between retrieval and generation multiple times. Recursive retrieval progressively refines results through multiple rounds. Here we see three augmentation patterns in detail. Iterative retrieval cycles between retrieval and generation steps. Recursive retrieval uses a tree-like structure to progressively refine information. Adaptive retrieval employs active judgment to determine when additional retrieval is needed. Evaluating RAG systems requires understanding key terminology. Context relevance measures how well retrieved information matches the query. Answer relevance assesses how well the response addresses the question. Faithfulness checks if the answer is grounded in the retrieved context. These and other metrics help us measure RAG performance comprehensively. Multiple metrics exist for RAG evaluation. Context precision, context recall, and context relevance measure retrieval quality. Answer relevance, faithfulness, and answer correctness evaluate generation quality. Aspect critique and answer similarity provide additional dimensions for assessment. This matrix shows which metrics apply to different evaluation aspects. Retrieval quality is measured by context precision, recall, and relevance. Generation quality uses answer relevance, faithfulness, and correctness. The end-to-end pipeline can be evaluated using answer similarity and aspect critique. Several frameworks have emerged for RAG evaluation. RGB, recall, and ARIS each target different aspects of the system. They employ various metrics like context relevance, noise robustness, and faithfulness to provide comprehensive evaluation across retrieval, generation, and overall system performance. The summary of RAG ecosystem is given in this slide. Downstream tasks, technology stacks, RAG paradigm and prospect, finally evaluation of RAG. Applications of RAG systems. RAG systems excel in enterprise knowledge management. They can search across internal documents, wikis, and databases to provide employees with instant access to organizational knowledge. This improves decision making, reduces time spent searching for information, and ensures consistency across the organization. The benefits include reduced human search time and improved consistency of answers. In regulatory research, RAG systems are particularly valuable. They can search through vast legal databases, case law, and regulatory documents. They help with compliance checking, legal research, and contract analysis, while maintaining accuracy and providing source citations for verification. Vector embeddings are crucial for RAG systems. They convert text into numerical representations that capture semantic meaning. Key packages for working with embeddings include OpenAI, Cohere, Sentence Transformers, Instructor, and Hugging Face Text Embeddings Inference. Building RAG systems requires the right tools. For document and knowledge storage, you'll need solutions to manage documents, embeddings, and indexes. Popular packages include Chroma, Pinecone, VV8, Qdrant, Milvus, and LanceDB. These vector databases form the foundation of your retrieval infrastructure. Retriever and orchestration pipelines handle the fetching of relevant documents based on query embeddings. LangChain and LlamaIndex are the leading frameworks for building these pipelines. They provide abstractions and tools to streamline the development of RAG applications. For LLM generation, you'll need APIs and tools to generate responses conditioned on retrieved documents. Options include OpenAI, Anthropic, Cohere, Hugging Face Transformers, and VLLM. These provide the language generation capabilities that complete the RAG pipeline. In conclusion, RAG systems represent a powerful approach to enhancing language models with external knowledge. They've evolved from naive implementations to sophisticated modular architectures. Proper evaluation using multiple metrics is essential. Real-world applications span enterprise knowledge management to legal research, and a rich ecosystem of tools makes building RAG systems more accessible than ever. Thank you for your attention.